Now let's study scalable k-means. The first extension we are looking at is called k-means plus plus. It was proposed in 2007, so that is 14 years ago. The key idea is to spread out the centers for initialization. How to do that? The procedures are first we will choose the first center uniformly at random. Right? So we will still pick the center randomly, but we only do this for the first center. And then for the following k minus 1 centers, for center 2 to k, we will choose the ith center to be a data point x0 sampled from a distribution computed like this. So just recall, this dxc means the distance from x to the closest center in C. What does this mean is for each data point, right? For each data point, we will compute a distance. And for each data point, we will compute the distance to its closest center in the current candidate centers. And then we normalize it by summing. This is some summation of all the squared distance. Then we normalize it, we will obtain a distribution. Right? So then we will sample from this distribution. By looking at the definition of this distribution, we will see a larger distance will have a higher probability to be sampled. That means we will choose the data points that is far away from the current centers in the set of centroids. So in this way, we are trying to spread out the centers. So in the original paper published in 2007, there is also a theorem to prove that this is a very good approximation to the optimal solution to k-means. So that is more technical, so we are not going over that. But if you are interested and good at math, you can visit that paper to learn. So again, let us go through an example to see how k-means plus plus do the initialization in a smart way. So the first step is still randomly pick one data point as the center, right? So this is random. It can be here, can be here, can be here, right? So it can be anywhere, any of these points. But what's different is now for the second centroid, we will compute the distribution. So this will be a centroid, right? The current set of centroid has only this point. We will compute for each other point, we will compute the distance and take the square, right? So then consider this as a distribution. Therefore, those points over here, right? So they have a large distance to the current centroid, right? So therefore, after taking the square, they will have very high probability to be sampled, right? So in comparison, these points, they are close to this center, right? So they are very close. So the distance is shorter. And after we square the distance, they will be much smaller compared to the square distance for these points. So they will have a very small probability compared to these points. Therefore, highly probable that the second centroid will be chosen over here, right? So therefore, it is highly probable that the centroid will be, second one will be chosen over here. And then for the next one, next centroid, we will look at, for this point, it will be the nearest, right? The nearest centroid. It will be this distance. And for this one, it will be this distance, right? So, and for this one, it will be this, right? So therefore, after considering these two centers, the one near this region, right? So it's basically the furthest from these two centroids has a higher probability to be chosen, right? So therefore, it is highly likely that the points over here will be chosen. And then for the fourth point, right? Fourth data point, we consider all these three current centroids. Therefore, the points over here, because they have quite large distance from all the three centers, but these points have very small distance, right, to the nearest centers, right? So you look at here, right? So these points have very close to the center, these also close to the center, right? So therefore, these three cluster points has a low probability to be chosen. And these points have high probability. Therefore, highly likely that we will pick the next centroid to be within this cluster. So this is a very smart way to spread the centroid over the data points. And this reminds me of the first few pieces that when you play the Go game, that you want to spread the stones so that you will take the most areas, right? So that's basically kind of spread, right? The idea is to spread out. However, k-means plus, although it's a very smart initialization scheme, but it has some limitations. K-means will need k passes over the data just for initialization, right? It's not yet for clustering, but just for initialization, you need to do k passes. And if we just have a small number of clusters, small k, that may be okay. But for big data applications, the k may be very large. For example, it can be 1,000, right? So then in this case, we need to do 1,000 passes over the data just for initialization. So therefore, this is slow and is not considered as scalable. So a promising solution was proposed about 5 years later. And the idea is that it observes that k-means samples just one point per iteration, right? So therefore, for k equal to 1,000, you have to do it 1,000 times, right? So that's a key reason is that it samples just one point per iteration. So the idea is, what if we oversample, right? What if we oversample by sampling each point independently, but with a larger probability and sample more, right? So sample more than just one point. We do oversampling. And this is actually equivalent to updating the distribution less frequently. And this is kind of coarser sampling. So basically, it is a kind of coarser sampling, and this leads to the k-means parallel algorithm, which was proposed in about 9 years ago, right? So 9 years ago in 2012. And both k-means plus plus and k-means parallel the authors are from Stanford. So they are from the same university, but it takes 5 years to go from plus plus to parallel. So let's take a look at how k-means parallel work. Suppose we have the same set of data points and we want 4 clusters. And suppose we specify an oversampling factor L equal to 3, right? So this is to say that we will sample 3 points at a time. And let's see how it works, right? So, but that is for the sampling state, right? For the first point, for the first centroid, we will still randomly initialize, right? So we will still start from random initialization. What differs is the following sampling stage, right? So instead of sample just one with the highest probability, we sample 3 points. We sample 3 points, right? So then, as we said, right? So these points have a larger distance than these points, so they have a higher probability to be selected, right? To be chosen. For example, if you oversample 3, then the next 3 points are highly likely to be over here, right? So for example, 1, 2, 3. And then we do another sampling, right? So we sample another 3 points, and they should be far from these existing centroid 1, 2, 3, and 4, right? So therefore, it is most likely to be over here, right? But here also have a little bit higher probability, right? So therefore, if you sample 3, is right. So here is far from over there, right? So therefore, the next 3 is this is random, right? So next time you run it, it may be different, maybe over here, right? So therefore, this is another 3 points, right? So, but now we have 1, 2, 3, 4, 5, 6, 7 centroids, right? But we just need 4, right? So what to do? So it's very clever, right? So they have very smart idea that then the next step is to cluster the intermediate centers, right? They will cluster these 1, 2, 3, 4, 5, 6, 7 points using k-means plus plus, right? After you cluster, because you have only 7 points, right? So it's much faster, right? So much faster to iterate through that points, and then you can quickly cluster them to have 4 centroids. So this is k-means parallel, right? So it was proposed in 2012. The procedure is you have an additional hyperparameter, right? So we need to choose the oversampling factor L, and it needs to be greater than 1, right? It needs to be greater than 1. And then we initialize the centroid set to be an arbitrary set of points, right? In the simple example, we choose 1, but you can choose an arbitrary set of points, right? It can be more than 1. And then we will iterate through the process. For our iterations, we will sample each data point in X independently. Right? So sample it independently with probability still the same as before, but multiply by a factor of L, right? So which is the oversampling factor, right? So we will sample each of the L points, right? So we sample each of the L points. I sample each of the L points according to this probability, and then add all the sample points to the set of centroids. And then finally, we will cluster the intermediate centers in C using k-means plus plus, right? Because we have only a small number of centroids in C, so this will be very efficient. And this k-means parallel has two major benefits over k-means plus plus. It is less susceptible to noisy outliers than k-means plus plus due to the oversampling and also a following clustering process. And it has also been shown that it will have more reduction in the number of Lloyd iterations. What it means is that it will converge faster than k-means plus plus. Right? So k-means plus plus has earlier been shown that will converge faster than the random initialization. And the k-means parallel will further speed up the convergence. Right? So this is to tackle the key limitations of k-means. The first one is slow to converge, right? So they basically k-means plus plus and k-means parallel are both faster to converge. And there is a very interesting interpretation of k-means parallel as an interpolation between the classical Lloyd algorithm and the k-means plus plus algorithm. So we look at the number of iterations R, and suppose we do not do the iteration at all, and we choose initially when we choose a centroid, we just choose k of them, right? So then that will be equivalent to Lloyd algorithm, right? So basically, there's no guarantees that this will be an approximation to the optimal solution because you may get stuck, right? You may get stuck. So if we do not do iteration in k-means parallel, we just, if R equal to 0, then we are just doing random initialization. So it is equivalent to Lloyd. And if we do a small number of R, that is the typical usage of k-means parallel. And in the paper, it has been shown to be guaranteed to approximate the optimal solution. And if we have R equal to the number of clusters K, and if we also have L equal to 1, right? So we said in order to be k-means parallel, we need to have K greater than 1, right? So this is talking about if we consider the degenerated case where L equal to 1, then if we do K iterations, then this version of this degenerated version of k-means parallel is exactly k-means plus plus. And you can verify that, right, from the distribution, because L equal to 1, right? Therefore, you are doing the sampling exactly as the way k-means plus plus is doing. And in this case, you have strong guarantee that this will be a very good approximation to the optimal solution, right? So that is the k-means parallel algorithm. 'Algorithm. 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 the introduction of the key algorithms. In the next section, we look at the k-means in Spark and the limitations of the k-means algorithm. Basically, are the limitations, right, that cannot be overcome by scalable k-means.